Okay, so we'll get started. So since there are a few people who are seeing this for the first time, and I'm hoping that you might have at least watched Professor Taha's lecture, so we'll start from this sketch. So this is the fuselage reference line. We draw the wing, we draw the tail. There is the CG of the aircraft somewhere in between. And then we start drawing the components that are important. So what is the first important thing? The oncoming free stream velocity direction. We can denote it by cap V or cap V sub dub. Dub is usually won't be mentioned, like whenever it's written as cap sub V, it's the incoming velocity stream seen by the main wing. Now, what's this? This is the incidence angle of the wing. So the wing is mounted onto the fuselage, not at 0 degrees, but at already positive incidence angle. And the angle made by the incoming free stream velocity with the wing is known as alpha wing or angle of attack at the wing. The next thing that would be of importance is forces and moments. So according to the simplified 2D airfoil theory, we are assuming approximating the airfoil with a 2D flat plate. So right at the quarter chord, we have the drag and the lift. The drag is parallel to the incoming free stream velocity. So this is drag on the wing. This and lift is perpendicular to the incoming velocity. So this is lift on the wing, and this is aerodynamic center of the wing. And finally, we'll have the aerodynamic moment about the pitching moment about the aerodynamic center on the wing. Okay. For reasons beyond my explanation, as I beyond my pay grade, I don't know why, but the community choose the origin at the leading edge of the airfoil. So you have to always remember that this is where the origin on the x-axis starts. Okay, and this is xac. So this distance is given as xac, or the distance of the aerodynamic center of the wing, and this is given as xcg. Great. Finally, we'll do similar artwork here. We have, so if this is V dub, like if this is V dub, the original velocity, then the velocity seen by the tail would be this or this. Anyone, the how many of you vote for this? How many of you vote for this? Okay, so downwash, this will be the answer. Why? Because as I explained yesterday, you have wingtip vortices coming out, which is going to induce downwash, and hence you'll see that the incipient velocity seen by the tail is slightly lower in angle of attack. So this is the incidence angle of the tail. This is the angle of attack at the tail. At the quarter chord point, we'll have drag on the tail, lift on the tail, and correspondingly we would have the aerodynamic center, and we'll have the pitching moment about the aerodynamic center on the tail. Okay. Does anyone have any doubt on constructing this diagram? Yeah. The leading edge of the wing, the point where the leading edge of the main wing. Okay, and then I'll translate this vector here. So if I were to see the V tail here, we would find that the angle between them is actually the downwash angle, which you might see just written down as epsilon or epsilon sub t. Downwash in our study is only going to be the downwash at the horizontal tail. It's like we won't be taking or going into detail into downwash at other places. So whenever you see epsilon written, it's going to be epsilon at the tail. And remember that epsilon at the tail is given as epsilon naught plus d epsilon by d alpha wing times alpha wing. Okay. So a short recapitulation from yesterday, that the entire objective of this simplified analysis in your first undergrad course for flight dynamics is that any force or moment that we'll write and any coefficient of force or moment that we'll write will always be expressed as like something like will always be expressed as m times alpha wing plus some constant. We are always trying to get this linear fit, assuming that the angle of attack is the input we can control on the wing. So whatever force, moment, coefficient of moment we want, our final goal is to cast it in this format. Okay. And you will see the usefulness of this format in the second half of the course. So you need to have some patience for that. Okay. Moving on. So I will be just writing down the results from yesterday, which was related to the wing. So we wrote down that the contribution, of the wing to the moment about the CG is roughly given as the moment about the aerodynamic center of the wing plus the lift at the wing times xcg minus xac. This approximation involves two primary things. If you can recall that, first of all, the small angle approximation, and the second aspect is that lift to drag ratio is always like greater than or equal to 10 in the passenger aircraft zone. So we can always, like, if we have a lift and drag term, we know that the lift term is going to be at least 10 times bigger than the drag term. So we can ignore it in certain cases. If you have not seen the derivation yesterday or not seen it on professor's lectures, recorded lectures, I strongly suggest you do this, because this will help you realize in a lot of situations that you don't need to keep track of all the terms. Like you must have seen yesterday, if you were there in yesterday's lecture, like it was bunch of like 4 terms times something plus 1. So there were like about 11 terms. And we like kept on canceling things to finally land up with 2 terms, which are important. So this is important in this subject. You need to develop an understanding of what to drop and what not to drop. Then we divide it, we non-dimensionalize it to finally get contribution of the wing to the pitching moment about the center of gravity as approximately, yeah, so you go ahead and basically non-dimensionalize this, and you'll get the coefficient of moment about the aerodynamic center for the wing plus the lift coefficient of the wing times xcg minus xac divided by c bar. Does anyone has any questions regarding this? How did we arrive here? Non-dimensionalization. There is literally no harm in asking a question. Like there's a lot of harm. Yes.
What does CG stand for again?
Center of gravity. So this is CG. So whenever now we are analyzing things for the entire aircraft. Okay. So whenever I am writing things for the aircraft, I will always denote it by CG. I will never, so you'll see contributions of wing, dub, contributions of tail, T, but for the aircraft, we'll always use CG. There is no A subscript. So when I say CG, it's the CG of the entire aircraft. Good question. Okay. And unknowingly, she has helped a lot of other people, because a lot of heads went like, oh, now I got this. Okay. Um, Everyone understood how we went from here to here, the non-dimensionalization? We divided, so to go from here to here, we simply divided by the dynamic pressure or dynamic head at the wing times the planform of the wing times the average chord length. So if you divide this entire equation by this, you would get the coefficient of moment about the CG. You would get the coefficient of moment about the aerodynamic center of the wing. And here, this part is going to non-dimensionalize and give you lift coefficient. And this part is going to, C bar is going to go underneath the distance. So this is all just recap from yesterday's lecture. Finally, as I told you that what is our end goal at the end of the day for each forces and moments? What form do we want it in? Linear form, where the variable of change is alpha at the wing. Now, have I obtained it in that form? No, right? Now let me see if I can. So this is going to be a constant, right? Because the coefficient of pitching moment does not change with angle of attack about the aerodynamic center. Simple 2D lifting line theory, okay? Not lifting line, simple 2D aerodynamic theory. And then you have CLW, like coefficient of lift at the wing. This is not a simple number because we all know that this can be written as CL naught at the wing plus CL alpha at the wing times alpha wing. Okay. So this part is constant, and all of you just remember that when I say naught, it means 0. Okay. So I'll say things like CL naught. Okay. I just don't have the habit of saying CLO or CL0 because the entire community is in the habit of saying naught. Okay. CL naught wing. So this is, and why is it called 0? Like why do I use 0? Any guesses? Why is this constant has a subscript 0?
Angle of attack is 0.
Yes, excellent. This is 0 and this is the only term that's left when angle of attack is 0. Okay. So this literally reads coefficient of lift at 0 angle of attack, or CL naught, plus CL alpha. So this is the coefficient which tells me that how does the lift change as alpha changes. Okay. Now this part is a constant as well. So this constant multiplies with this constant to give me a constant, and this is already a constant. So I will rearrange the terms a little bit to finally write and then this is multiplied with alpha. So I will write CL alpha of the wing times XCG minus XAC by C bar times alpha wing. So now can you see that pattern? And this is your final result. Contribution of the wing about the pitching to the pitching moment about the center of gravity expressed as the form we want. Any doubts? Okay, so we'll do similar things for the tail now. I won't go into the complete details of the derivation, like resolving the forces and blah blah. So you all know that now basically you will, just like the way we did here yesterday, I made a mistake in this, so I'm again pointing it out. So when you wanted to write the moment contributions for these forces and moments about the CG, you would recall your concepts from MAE 80, you simply transfer the moment, okay? And then you need to multiply the force with the moment arm. So it's better to decompose it into vertical and horizontal components. And we know that the moment arm for the vertical component is going to be xcg minus xac. This is where this came from. And the moment arm for the horizontal forces is going to be delta z, which we ignored because delta z is going to be much, much smaller than xcg minus xac, okay? And then you to decompose it, you would need this angle. Now, how would you get this angle? We need to trace back here. So this is the velocity of the incoming airstream. I'll drop a perpendicular here. So now this perpendicular must be parallel to the lift because lift is perpendicular to the incipient airstream. So if this is angle beta, then actually I should not call it beta. Let's call it angle question mark. We'll be using a lot of symbols later on, so I don't want to confuse you. So this is question mark. Okay, no issues. Now I'll extend this line along the incipient airstream. Okay. Now this plus this is 90, right? Because they're perpendicular. So this is pi by 2 minus question mark. Now this and this is total 90, right? Which means that if this is pi by 2 minus question mark, this is question mark again. Which means that the angle opposite is going to be question mark as well. And you will see that question mark plus I dub is equals alpha dub. Which means that the angle that we are looking for is alpha dub minus I dub. Okay. So similarly, now what will happen is let's go and write the contributions for the tail. Okay. Yes.
I thought if we, like, for instance, extend the bottom line and then like to make it parallel to the FRL, and then like so that angle that angle is going to be equal to the top angle, right? Like the alpha.
So you realize that, like, let's go the other way around. Okay. You realize that this angle here is alpha minus I for the wing.
Yes.
Now, if this angle is alpha minus I, then this angle is going to be alpha minus I.
Okay.
Okay. Agreed?
Okay.
Now, if I drop a perpendicular, this angle is going to be pi by 2 or 90 degrees minus alpha minus I.
Okay.
Now, forget about this. Now, let's look at this and this.
Yeah, but how do we know that's right angle?
Because it's by construction. Like, I dropped this perpendicular and this perpendicular is parallel to the lift vector. The lift is perpendicular to the incipient airstream. You agree this? You agree with this?
Yeah, can you repeat that?
The lift is perpendicular to the oncoming airstream velocity.
The lift is perpendicular to the incoming air, right?
Yes,
Okay,
at
yeah,
the
yeah,
wing.
right.
So I have just translated the same direction here. So it's like this from geometry. Like, for example, if you had two parallel lines and if you drop a line like this angle and this angle are the same.
Yeah, of course.
So it's the same thing. So this is the V stream and this is the lift.
Okay.
So I am just translating it here again.
That's fine.
So if this is 90, like if the lift and V wing are making 90, so it's like lift with V wing is 90. This with V wing will also be 90.
Okay. Yeah, but like I just saw like if you do the other way, it's like a different answer, like in a sense. Like I just saw if we do the other way, like extending the bottom line, like you need to subtract another epsilon.
Oh no, that's epsilon doesn't even come into the picture here. Do you mind if we discuss this like right after the class? Because like this is math. It's not going to come out a different answer if you do it the other way. So just for the sake of time, I'll take it with you in detail at the end of the class. Okay?
Okay.
Okay, sure. So now let's take up the tail contributions. Is this only his doubt, or like is this a doubt for majority of the people? So right now just have a leap of faith that this is alpha dub minus I dub. I'll show you how to find out. Okay. Now for the tail, same things. Contribution of the tail to the moment about the CG is roughly equal to, or let's say exactly equal to. So we'll transfer the moment as it is. So we would have moment about the aerodynamic center for the tail, on the tail, and then we would do similar stuff. So you can again find out that it will come as no surprise that this is alpha tail minus I tail. Okay, just like that was alpha wing minus I wing. So you will write down the same equation where you will take the horizontal component of the lift. I don't know, you can do this on your own as we did yesterday. Then you will multiply it with this distance. Which distance? This is L tail. Okay, this is the distance from the CG of the airplane to the aerodynamic center of the tail. Okay, L tail is x, I should write it like this, x AC of the tail minus x CG, magnitude. L tail is a positive number. Okay, moving on. So you will have, and obviously there is some delta Z tail. Okay, so you will have some horizontal. So this is basically the vertical component plus some horizontal component times delta Z. And just to be cautious, again, here you'll see that the vertical forces, if I take the moment, right, what's happening? Their moment is making the aircraft pitch down. So it's negative moment. Okay. So this would be negative LT. You will again make the same approximations that we made in yesterday's lectures. Small angle lift is much, much greater than drag. Cos of a small angle is roughly equal to 1. Sine of a small angle is roughly equal to 0. And you will ultimately land up with a very straightforward equation that the moment contribution of the tail to the pitching moment about the center of gravity is approximately moment pitching moment about the aerodynamic center of the tail minus lift at the tail times L tail. Okay. Now, as a simplifying assumption, we assume that the tail's major purpose is not to enhance the lift on the aircraft, it's to provide control over pitch. So we use symmetric tails. And for symmetric tails, I told you, like I showed this yesterday, so let me draw it up here. So let's say this is a symmetric airfoil, right? And how does the pressure distribution? I told you that these are rigid bodies. So you have a distribution of forces, something like this. Such that this distribution is exactly identical as it is on the upper surface and the lower surface. The only difference is the direction is reversed. So you get, first of all, you get zero lift, right? And because it's absolutely symmetrical, you go to the aerodynamic center and you take the moment. If everything is acting in the opposite direction, the entire moment is also going to be zero, right? And then we know that the moment of a 2D cross section of an airfoil does not change with angle of attack if the moment is written about the aerodynamic center, which means that if the moment for a symmetric airfoil at zero angle of attack is zero about the aerodynamic center, the pitching moment about the aerodynamic center for all angles of attack is? Why do I hear only one person say the answer? Let's do the exercise again, okay? I'll do it slowly, but get this into your heads. The main job of the tail is not to enhance lift on the aircraft. Lifting the aircraft is wing's job. Tail is there so that we don't end up in a Boeing 737 like situation. And now we'll have symmetric tails, okay? Because we'll deflect these tails to get small amount of forces which will multiply with this large moment arm to give us huge moments, okay? This huge, that is why the tail is right at the back of the aircraft, okay? It's for the moment arm. Now, for a rigid body, especially in fluid flows, like when you have millions of air particles running over the wing, there is a continuous distribution of forces. At each point, there is a small amount of force acting. And when you sum that up or you integrate it along the entire body, you'll get a total lift or drag, right? But for a symmetric body, you have exactly, so let's say there is a small amount of force here, there would be exactly a same strength and like flipped out direction. Like it's a mirror image of the force distribution at the top. Okay. What happens? This cancels out. So let's say this had a component like this and this had a component like this. So the vertical components will cancel out. Okay, there's no lift. There also not be any pitching moment. Got it? So when the pitching moment is 0 for other angles of attack, it's also going to be 0 because about the aerodynamic center, the pitching moment does not change. So what is going to be MAC tail? Okay, acceptable. So we can assume that it is 0. So the only term now that's left is negative LT, cap LT, small lt. Let's expand this to see that even though we have a single term, we still are in a little bit of trouble. Why? Half rho v square. Now this is lift at the tail. So this will be half rho v square at the tail or at the wing? Area of the tail, lift coefficient of the tail times L tail. Okay. Now again, so before I non-dimensionalize, same exercise. This is our target form in the linear form. And what's the variable there? Read it very closely. It's alpha wing. Okay. So now the only term that's going to give me some dependence on angle of attack is this CL wing, CL tail, sorry. And you write it down as CL naught for the tail plus CL alpha for the tail times alpha at the tail. Okay. So we are done. Why?
You have to relate the tail angle of attack to the wing.
Yes. So now I can't look at this. This is alpha at the wing. This is alpha at the tail. And alpha at the tail and the wing are not the same things. They're different. So we need to relate alpha at the tail and alpha at the wing. Okay. So let's do that. Let's move backwards. So everybody, no one looks into their notebook right now. Okay, you can all watch the video later on, but see, this is geometry. You need to see. This angle is alpha tail minus I tail, which means that this angle would be alpha tail minus I tail, parallel lines. Now I will draw this picture in a neater format. Okay. So you have the incipient airstream at the wing. You have the incipient airstream at the tail. This is the downwash angle. This is the horizontal or the fuselage reference line. And this is the vertical. Okay. We have already found out the angle between V tail and the horizontal, right? It's alpha tail minus I tail. The only angle that's left is this, We kind of know it already. So this angle here is what? Huh?
It's alpha wave.
Yes, so this angle here is the angle that V dub is making with the vertical. So the angle that V dub makes with the horizontal is alpha wing minus I wing. And this is a right angle triangle. So this is going to be pi by 2. No, I did not succeed. This is V wing. This is the wing, right? This is the horizontal line. This is I wing. This is alpha wing. Yes.
Pi over 2 minus the question.
Yes. So this angle here is alpha wing minus I wing. Is everyone with me until here? Now I'll drop a vertical here and I'm looking for this angle. This angle is 90. Is everyone with me until here? The sum of the angles inside a triangle is? Excellent. So pi is equals to pi by 2 plus alpha wing minus I wing, and let's call this double question mark plus double question mark. So which means that double question mark is going to be pi by 2 minus alpha wing plus I wing. Anybody objects to this? Or is not feeling confident that they can derive this on your own? Ask it right now. You can do this. I know it's overwhelming, but you need to sit with a pen and paper. You're seeing it for the first time. Don't worry. Okay, so now this angle is going to be pi by 2 minus alpha wing plus I wing. Okay, which means that this entire thing is 90 degrees, right? Which means that pi by 2 is equals to, oh, you guys know that pi by 2 is 90 degrees. Like I am writing this in radians. So this is like 90 degrees, okay? And most of your angles will be in radians. So be careful when it's given in degrees and convert them to radians. Pi by 2 is equals to pi by 2 minus alpha wing plus I wing and plus epsilon plus alpha tail minus I tail, okay? Which essentially boils down to writing, so now we need to write alpha tail in terms of alpha w. So we'll shift everything the other side. So we have alpha tail is equals to alpha dub minus I dub minus epsilon plus I sub t, okay? Are we done? You need to ask yourself this question a lot of times in this course. So, okay, I wanted this. Fantastic. This is constant, this is constant. Is this a constant? Okay, it's not. So we need something further. We need to substitute this thing here. And then we would get alpha dub common 1 minus d epsilon by d alpha minus epsilon naught minus I dub plus I tail. This part is the constant and this part is multiplied with alpha dub. Okay. So finally, we can write here that CL tail is equals to CL naught tail plus CL alpha tail times alpha tail, which is going to be CL naught tail plus CL alpha tail multiplied with this constant part is going to give you another constant. So it's CL alpha tail times minus I dub minus epsilon naught plus I tail, and CL alpha tail multiplied with this part is going to give you the coefficient for alpha dub. So plus CL alpha tail 1 minus d epsilon by d alpha times alpha wing. So now, by the grace of God, this is the constant part and this is your slope and this is alpha dub. Anyone, any doubts up until now?
Okay, so how did you form that identity? Like, if pi over 2 equals to the rest angles.
This one?
Yeah.
So this is perpendicular, and the total angle is going to be 90 degrees.
Yeah.
And then I found out each of the three pieces one by one.
Okay, so you're claiming the bottom one is still okay. Yeah, okay. That one, yeah, that one. I think we said we chat around the end. Yeah.
Yes.
Okay.
I mean, it's very genuine. Like, you have to, at least from my experience, when I was an undergrad kid, I did it like 2 times or 3 times with my hand to finally internalize it. And it takes time. You'll do some questions, you'll do some geometry, and then you'll get a hang of it. It's okay to feel overwhelmed in the first class.
And then are you taking the derivative?
Oh yes, this is directly coming from the relation here. Like, this should be given to you. You won't have to like calculate the derivative or something. This is an experimentally derived entity, or it will be provided to you. Like, you won't be given a function that you have to differentiate and get something. It's a factor that will be given to you. Yep.
The coefficient or CL naught t, would that be 0 or would that not be 0?
Oh yeah, I'm getting there.
Oh,
Yes, he is absolutely correct. So we can make a further assumption here that because the tail is going to be symmetric, this will also be 0. Okay. So now let's clean things up a little bit. And also, you don't need to memorize the results. Like, you need to write it down somewhere, you need to catalog it. You will be allowed 2 sides of like formulae sheet in the midterm and final exams. The important part is like seeing what I am doing, like trying to ultimately reach that thing. Your ultimate goal is always going to be like, you'll be dropped somewhere in the problem and we'll tell you that go get that. Okay. Yep. So what is the next logical step?
non-dimensional.
Non-dimensionalization. Okay. So I'll also write this down. By the way, I'll discuss this in more detail in the next discussion session, but this should be your kind of attack trajectory. Like, sort out your unknowns and knowns, draw the figure, get the equations of motion, non-dimensionalize, get it in terms of y equals m alpha plus c. Okay, this will simplify. If you think in this manner, this is what we have been doing actually. First of all, I write down my knowns and unknowns. Like, here it became a part of the figure. These two things will kind of happen together. Like, you draw the figure and you write down that, okay, alpha dub is given to me, I dub is given to me, I tail is given to me, so on and so forth. Then you go ahead and write down the equations of motion. These are nothing else but simplified equation of momentum. That's all, right? And then you go ahead and non-dimensionalize and get your final forms. Okay, so you go ahead and non-dimensionalize, and you're going to non-dimensionalize by the airplane's parameters. And as we mentioned yesterday, it's going to be the same as the wing parameters, divided by half rho v square at the wing, s wing, c bar wing. Now let's see what happens here. So we have negative half rho v square at the tail divided by half rho v square at the wing. Then we have S tail. I'll shift this small L tail before, and then we have S wing, C bar wing times CL tail, which is this monstrosity here. Okay. So everybody followed me up until here. Now I'll tell you why I wrote it this way, because can we cancel this and this? No, because the velocity seen by the tail and the velocity seen by the wing are not going to be the same. The tail experiences a different velocity because of the downwash. So we don't cancel it out. It's very close to 1, but like a very important reminder that it won't always be in practicality. So we call this fraction as tail efficiency, eta. And if it's not given to you in your question, feel free to assume that eta is either 0.9, somewhere between 0.9 to 1.0, if it's not given. And if you like, just choose one whenever it's not given, but you should write it down that I'm assuming eta is 1. Okay, don't, if you do cancel and write 1, half a mark. Okay, then the next, so you'll see here, these are completely different terms. This is the planform area of the tail. This is the moment arm from the CG of the aircraft to the aerodynamic center of the tail. This is planform area of the wing. This is mean aerodynamic chord of the wing. Nothing is going to cancel here. But we club these terms together to call it the horizontal tail volume ratio. Horizontal tail volume ratio, also denoted by cap V sub cap H. Okay. So finally, if I were to write it down in terms of these, what would I have? I would have contribution of the tail to the coefficient of pitching moment about the center of gravity approximately equal to, don't forget there is a negative sign here, negative eta tail, actually this should be written as tail, eta tail times horizontal tail volume ratio times CL tail, and CL tail is this entire thing. So you can actually take CL alpha tail as common, and then the constant part is negative I dub plus, oh sorry, negative I dub minus epsilon naught plus I sub t plus 1 minus d epsilon by d alpha wing times alpha wing. So this is the final result that we were looking for. Okay. Any objections, any questions? No leaps of faith for the final equation. It should be crystal clear. If we are good, then I'll pick up the final piece of the discussion. And I would suggest that you write these 2 questions as just questions in your answer, in your notebook right now, and just try to follow along and go and write down your own answer later on. So is everyone done writing? I'll wait for a minute or so if you are not, because the last 2 questions are like crucial, you understand them. After I see all heads up, I'll do that. Yes, so the tail efficiency is the ratio between the dynamic pressure head on the tail divided by the dynamic pressure head at the wing. So this term half rho v square, in some books you will also see it written as Q. So it is written as Q sub T by Q sub W. Okay, lot of notations. It's just the dynamic, the pressure energy in the kinematic, like in the flowing part of the flow, not in the static part of the flow. So at the tail divided by at the wing. So it's called tail efficiency because it's telling you that in a very crude manner, if I had to explain that if you had like lesser downwash, like huge wings but smaller tail, you would see less downwash and you would generate more force at the tail. So it would be more efficient in controlling the entire aircraft. But because of the downwash, we experience some loss of velocity, which leads to loss of force, which leads to loss of moment. But like there is a lot of nomenclature I myself have questions about, but born too late. So everyone look up now. And finally, the final piece is like we now look at the entire aircraft. And we saw that Wing and tail are the two main contributors here, right? And you can do similar analysis for the lift and drag as well. Like we didn't do an analysis like this for lift and drag, okay? Because first of all, in Professor Taha's first lecture, if you remember, drag is not a central theme of this course. That's the central theme of 158, performance, okay? Drag is way less than lift, so we don't consider it here. And second, like you can say that like 70 to 85% of the entire lift or entire forces on the aircraft is solely responsible, like solely coming from the wing, not the tube, not the horizontal tail, not the vertical tail. So we don't do much of force analysis because forces, what will you do? You'll just go and decompose the horizontal and vertical, and you'll take the small angle approximation, and ultimately you'll end up with the term that the lift on the entire tail is the lift on the lift on the entire aircraft is the lift on the wing. Okay, so it's a frivolous exercise, but pitching moments are important. Why? So now for the entire aircraft, I can write down the pitching moment about the center of gravity as some constant plus some coefficient for the alpha wing, right? I mean, I showed you, right, that this is the contribution coming from the wing, this is the contribution coming from the tail, right? They both have their individual constant and coefficient parts. So there will be parts coming from the wing and tail in the constant, and there will be parts coming from the wing and tail. So this is nothing but delta dub Cm Cg naught plus delta T Cm Cg naught is equals to Cm Cg naught. Okay, and if you analyze, like let's say you started working at a company which wants to make a biplane. So now you don't have one wing, you have two wings. So you will go and analyze the contribution of the top wing and the bottom wing. Okay, something like that. Let's say you are working for a Formula SAE car. So now they have something like this on their rear windshields. So you go and analyze the contribution of the first wing, second wing, and the third wing. The steps are still the same. Okay, the better you are, the more the money you make. So now the question arises, like whether this should be positive, negative, or zero, or whether this should be positive, negative, or zero, right? Let's deal with the first graph first. So let's deal with this part first. Like, what are the two options that we have? The two options that we have are that this is CMCG, this is alpha wing, and then here we have CMCG alpha negative, and the other one we have, I mean, 0 is going to make no sense, so we are going to discard 0, and then we have CMCG with respect to alpha positive. So what does this mean? Now look at this. You had an aircraft okay, flying, and this was the incipient airstream velocity. You were flying at some angle of attack, and suddenly, right now we have not discussed any controls. We are not giving any inputs. We are just observing it as a passive system, right? As in, if we give it a disturbance, what will the system do on its own without a pilot, right? So suddenly a thunderstorm comes and a gust of air hits the aircraft like this. Now what happens? Suddenly you experience a huge angle of attack, right? So let's say that we were operating somewhere here as an angle of attack, and then after disturbance we came to this angle of attack. So now what happens? If I travel along the red curve, the pitching moment increases. If I travel along the blue curve, the pitching moment decreases. Now what do I want? Like, remember that pitching moment is this way positive. So my alpha has already increased, and I don't want to increase alpha too much. Why? Because I'll hit stall, right? I don't want to hit stall. I want to be in the safe operation region. So I want to come back to a lower alpha. Which curve is going to help me get to back to a lower alpha? The blue one, okay? So this is the gospel of flight dynamics. Cm, Cg, alpha should be negative for the entire aircraft, okay? There are some few aircrafts which have CMCG positive and they are like actively controlled. Those are fighter jets, but that won't be the central theme of this course. Passenger aircraft, CMCG alpha or CM alpha negative. Okay, etch this into your brains. Like even if you are in your sleep and someone like wakes you up and asks, should CM alpha be negative or positive? You should be able to say it should be negative, because this is like the most fundamental pillar of stability in flight dynamics. If your design does not have CM alpha negative, it's not a inherently stable design. Okay. So we found out one piece of the puzzle, that this has to be negative. Now what about this? So now, okay, we got this and like we know that this is discarded, but this is negative too, right? This is your intercept here, Cm Cg naught, and this is your intercept here, Cm Cg naught. At one place it's positive, at one place it's negative. Which one do you desire? Why?
You can generate enough lift to overcome the weight of the air.
Yes. So like I did this in the morning as well, but you guys guessed it better. So there is no sense in looking at these points actually. Forget about this axis, look at this axis, right? What does this axis, the angle of attack axis, represent? If I am at any point on this axis, what is my total moment on the aircraft? 0. And when you are cruising stably, what is the total moment that you want on your aircraft? 0. Which means all of these points denote points of operation at which you can cruise. Now you have to decide what's realistic, what's unrealistic. We generally have positively cambered airfoils, which means that they need to be at some positive angle of attack to generate lift. And in cruising, you need to balance your weight with lift. So obviously you need a positive angle of attack. With a negative CMCG naught, you will have a negative alpha operating point. With a positive CMCG naught, you will have a positive alpha operating point. Which one will you choose? The positive one. So this has to be greater than 0. So these are the two central tendencies. And now if you look at it, finally, just the last thing, look at this. So wing is the one which is generating the most amount of lift, right? But look at its contribution to like the constant part, first of all. It's positive, that's good. But does this make it positive? The CM alpha part? Like, no need to rush. It's just a 2-minute concept. I'll leave you. I know I'm a little bit over time. I'll leave you. So this is the constant part. This is all positive. Here, like this is, we don't know exactly because there is a lot of plus and minuses involved, but be assured that the values here are much bigger as compared to the tail, so it will remain positive. So we have a positive coefficient here. We are good. But we want CM alpha to be negative. The part that's coming from lift, it is not negative. From the wing is not negative. It's positive. And the tail will have to be sized, positioned, and made in such a manner that this entire product becomes negative and negatively large enough so that the entire sum is negative. So always remember that the wing, even though carries you in the air, it causes a destabilizing effect on the entire aircraft. The tail, even though it's not carrying your weight, it's causing destabilizing effect on the aircraft. Okay? Go home.